In this video, we're going to go over example 1214, where now we're going to look at the electric field created by a point charge that is moving in uniform motion. So you're going to have some charge Q, which is now going to be moving in with some velocity V. And we want to see what is the electric field. If it was just at rest, we'd know that the electric field would just move out radially and follow Coulomb's law. So now we want to figure out what it's going to look like while it's moving with a velocity. And so the frame we're going to start with is the S frame, where the S frame is at rest, and the velocity is v0 with respect to that S frame. Okay, so we can measure the position of the charge, and we can also measure the position of the electric field at some point out here. Okay, so I'm going to call that that distance basically, for all intents and purposes, we're going to try and make this as easy as possible. So really we can call that distance R0 from the charge to the electric field. Okay, so now if we were to work it out, and I guess the book calls this the S0 frame since we're calling the velocity V0 and the distance R0. So the electric field E0 is going to be 1 over 4 pi epsilon naught Q, and then R0 squared in the R hat 0 direction. Now, what we can do is we can look at the components of it, and so we can write down the components. So EX0 is going to be 1 over 4 pi epsilon naught Q over essentially x0 squared plus y0 squared plus z0 squared, all to the 3/2 power, because they have to take into account the magnitude of the distance, which is inside the vector direction. Okay, so we can write down the y component similarly. Oh, I'm sorry, this is in the x0 direction. So that's why we have the extra 3/2, because we can put an x0 up there. This would be y0 and then z0 is a similar equation. Okay. So the reason I wrote out all 3 directions is if you think back to the previous video lecture where we looked at the parallel plate capacitor, where it is moving with some velocity v0, what we found was that you know the dimension of the capacitor would contract due to length contraction, but the electric field is perpendicular to that length contraction. But the electric field is proportional to the charge density, and since the charge density gets modified because of the length contraction, the perpendicular component of the electric field in a frame, say S bar, is going to be gamma 0 E0 perpendicular. So it's the perpendicular component of the electric field that gets modified by special relativity, even though the electric field is not in the direction of the motion. The parallel components do not get modified. Okay, so that's important because that would mean that since let's say that the direction of motion is in the x direction. That would mean that the x component of the electric field would not be modified, but the y component of the electric field would, and the z component would, because those are perpendicular to the direction of motion. So again, what I'm saying is that v0, I'm arbitrarily defining to be in the x direction. Okay, so our y component and z component get modified by special relativity because they are the perpendicular components to the velocity. And just to remind everybody what the gamma factor is, like that. Okay, now, okay, so the fields, the perpendicular components of the fields get modified, but the coordinates are the ones that are in the direction of motion get modified by special relativity, and the perpendicular coordinates do not. So therefore, x0 is going to be gamma 0 x plus v0t from the Lorentz transformation. And I'm just going to call that gamma 0 rx. And then y0 is equal to y, which is equal to ry. Z0 is equal to z, which I'm going to call rz. So I'm just using the r's because it's going to be a lot easier to carry around that than have to keep writing x plus v0 times the time. Okay. So this r vector is a vector from the charge pointing to a point in space where we're measuring the field. So let's redraw our coordinate system. And if this is x, z, and y, our charge now is on the x-axis, moving with some velocity, and we're picking a coordinate or vector r, where we're going to measure the electric field out here at that point. So this r vector is basically some angle theta with respect to the x-axis. So what I could say is this coordinate right here, q, has moved from the origin by a distance of minus v0t. Okay, so now let's rewrite those electric field components right up here, not in terms of x, y's, and z's, but in terms of r's. And so we'll now write it for the, what I guess we would call the S bar frame. So basically we've moved such that we've moved into a frame where now the charge is going to be considered stationary and the frame itself is moving with a velocity v0. So that's what frame, I guess we can call it S bar, is q at rest, and the frame itself is now going to be moving with a velocity minus v0. Okay, so now the electric field component, electric field in the S bar frame, okay, so now we're converting over, and we're going to write it in terms of spherical coordinates now that we're using r's, is 1 over 4 pi epsilon naught gamma naught q times r vector divided by gamma 0 squared r squared cosine squared, so that you can say would be the x component, plus r squared sine squared theta. Okay, so this is the x component, and this is the y and z components right here. So I could actually write it that way. Okay, so we've converted this now over to spherical coordinates. You notice that I'm using the vector r right here and not writing it down in terms of x, y, and z components. And that's because we get a gamma 0 on every component. One of the gamma zeros for the x component comes from the contraction of the coordinate system, and the gamma 0 for the y and the z components electric field come because they get contracted because of the electric field. The perpendicular components of electric field are the ones that are modified. Okay. Okay, so let's rewrite this now. We can factor out the r squared from the denominator. And what we get is 1 over 4 pi epsilon naught gamma 0 q. If I factor out an r squared, that would give me r cubed. And so I'm going to be left with gamma 0 squared cosine squared theta plus sine squared theta to the 3/2 power times r divided by r cubed, like so. So I can now, let's see, factor out a gamma squared out of the denominator. So that would be giving me a gamma 0 cubed cosine squared theta plus sine squared theta divided by gamma 0 squared. All of that to the 3/2 power. And since I have r vector over r cubed, I could turn that into an r hat over r squared, like so. And now, let's see, if I take a look at this, I can cancel one of the gammas, make this a gamma squared, and I can also now put in what I have for 1 over gamma squared. 1 over gamma squared is just 1 minus v0 over c quantity squared. So if I do that, my electric field now looks like 1 over 4 pi epsilon naught. And I get a 1 over gamma squared q cosine squared theta plus 1 minus v0 squared over c squared sine squared theta 3/2 r hat over r squared. Okay, so you can probably see where I'm going with this. If I now multiply the sine squared through those parentheses, I'll have a cosine squared plus a sine squared. And so I can now rewrite this as 1 over 4 pi epsilon naught. I'm going to bring that 1 over gamma squared back up and put it in the numerator. So therefore I get q times 1 minus v0 squared over c squared. I now have 1 minus v0 squared over c squared sine squared theta to the 3/2 power times r hat over r squared. Okay. Okay, so I'm going to stop here and basically say this is the end result of the electric field that you would measure in the S-bar frame. Now what we have to consider is the magnetic field. So in the next lecture, I'll continue this discussion by incorporating now in the magnetic fields.